Welcome to the Robert Joodat Podcast, where intelligence sharpens in the dark. Research-driven, human-verified. Stay curious.
Right now, your phone knows exactly where you are on a planet of 8 billion people, pinpointed from roughly 20,000 kilometers up in space, and it did that without you lifting a finger or sending a single signal anywhere. Today, we're pulling back the curtain on GPS, how the system is actually structured, the surprisingly elegant math that puts a blue dot on your map, and why that dot is sometimes a little off. By the end of this episode, you'll understand what's really happening every time you ask your phone for directions. And to break all of this down, I've got someone who genuinely loves this stuff. So let's get into it. Walk me through what GPS actually is at its core.
So GPS, Global Positioning System, is a satellite-based navigation system that provides real-time location, speed, and time data. And the key thing to understand up front is that it's not one thing. It's three things working together, what the system calls segments.
3 segments. Okay, break those down for me.
So you've got the space segment, which is the satellites themselves. Then you've got the ground control segment, which is Earth-based monitor stations, master control stations, and ground antennas that track and operate the satellites. And then you've got the user segment, that's the receiver in your phone, your car, your watch, whatever device is listening for the signals.
So my phone is just listening? It's not talking back to the satellites?
Exactly, and this is one of the most underrated facts about GPS. It is completely passive. According to a 2026 guide on how GPS works, GPS is a passive technology. Your device only receives signals. It never transmits anything to the satellites. The satellites have zero idea you exist.
Wait, so millions of people can use GPS at the same time and the satellites don't care?
Not even a little bit. There's no congestion, no login, no account. It's free, it's global, and it's always on. The US Space Force maintains it, and the system is available to everyone worldwide at no direct cost.
That's kind of wild when you think about it. Okay, so how many satellites are we actually talking about up there?
Right now, there are 31 operational satellites. They orbit in 6 Earth-centered orbital planes, each with 4 satellites, sitting about 20,180 kilometers above Earth, and they're moving at around 14,000 kilometers per hour. According to Wikipedia's GPS entry, each satellite completes an orbit in about 11 hours and 58 minutes.
So they're just constantly lapping the planet.
Constantly. And the ground control segment is always watching them, using radar to verify they're actually where they're supposed to be. NASA describes it really well. The satellites act like stars in constellations. We know where they're supposed to be at any given time, and the ground stations confirm it.
Oh, that's actually a beautiful analogy. And speaking of stars and navigation, this goes back way further than most people realize, right?
Way further. NASA points out that humans have looked to the skies to find their way since ancient times. Ancient sailors used constellations to figure out where they were and where they were going. GPS is literally the same concept, fixed known points in the sky, just way higher up and way more precise.
So we went from Orion's belt to a constellation of 31 government satellites. That's quite an upgrade.
And the origin story of GPS is genuinely fascinating. It actually traces back to Sputnik. When the Soviets launched Sputnik in the late 1950s, American scientists realized they could track it by observing shifts in its radio signal. That's the Doppler effect. And that observation became the seed of the whole idea.
So the Cold War accidentally gave us Google Maps.
Kind of, yeah. According to NASA's history of GPS, the US Navy ran satellite navigation experiments in the mid-1960s specifically to track submarines carrying nuclear missiles. With 6 satellites orbiting the poles, submarines could observe Doppler changes and pinpoint their location within minutes.
Nuclear submarines. That's a very different use case than finding the nearest coffee shop.
Very different stakes. Then in the early 1970s, the Department of Defense decided they wanted a more robust, stable system. They launched the first Navstar satellite in 1978, and the full 24-satellite system became operational in 1993. That's the foundation of what we use today.
And it cost a lot to build, I'm guessing.
According to Wikipedia, the initial constellation cost around $12 billion, and it currently costs about $1.84 billion per year to operate as of 2023. And yet it's completely free for anyone in the world to use.
$1.84 billion a year, and I've never paid a cent for it. Okay, so now I want to get into the actual mechanics. How does the system figure out where I am?
This is where it gets really elegant. The core concept is called trilateration. According to GPS.gov, trilateration literally means positioning from three distances. The idea is that if you know your distance from three known points, you can figure out exactly where you are.
Okay, but how does your phone measure its distance from a satellite that's 20,000 kilometers away? Great question, and this is the clever part. GPS.gov explains it using a simple formula: distance equals rate times time. The satellites are constantly broadcasting radio signals. Those signals travel at the speed of light, 299,792,458 meters per second. Your receiver measures how long it took for the signal to arrive, and from that, it calculates the distance.
So it's basically timing how long the signal takes to get to you.
Exactly. The FAA describes it this way: the receiver uses the time difference between when the signal was broadcast and when it was received to compute the range from the receiver to the satellite. Do that with 3 satellites and you've got a position on Earth's surface.
But you mentioned 4 satellites earlier. Why 4 if 3 is enough? This is the part that really blew my mind when I first understood it. 3 satellites give you a position on the surface, but there's a problem. Your receiver's clock isn't perfect. To calculate distance from signal travel time, you need incredibly precise timing. GPS satellites carry atomic clocks. Your phone does not.
Right, because atomic clocks are not exactly pocket-sized.
Not even close. So the 4th satellite is used to correct the receiver's clock error. According to the FAA, by taking a measurement from a 4th satellite, the receiver avoids the need for an atomic clock entirely. The 4th satellite also enables calculation of altitude, which moves you into 3-dimensional positioning: latitude, longitude, altitude, and time.
So the 4th satellite is basically doing the job of a multi-million-dollar atomic clock. That's genuinely clever engineering.
It really is. And according to Geotab's breakdown of GPS, the satellites themselves orbit at 13,000 miles above Earth and travel at 8,700 miles per hour. The precision required to make all of this work is staggering.
Okay, so let's talk about accuracy, because I know my phone has definitely put me on the wrong side of a building before. How accurate is GPS actually supposed to be?
So the FAA states that the basic GPS service provides approximately 7-meter accuracy, 95% of the time, anywhere on or near the surface of the Earth. But GPS.gov gets more specific. GPS-enabled smartphones are typically accurate to within 4.9 meters, about 16 feet, under open sky.
Under open sky. That qualifier is doing a lot of work.
It really is, because accuracy degrades significantly in urban environments. GPS.gov lists the common causes: satellite signal blockage from buildings, bridges, and trees, indoor or underground use, and something called multipath distortion, where signals bounce off buildings or walls before reaching your receiver, which throws off the timing calculation.
Oh, so when my GPS puts me in the middle of a river in a city, it's probably multipath?
Very likely. According to the Wikipedia error analysis for GPS, ionospheric effects alone can introduce errors of plus or minus 5 meters. Ephemeris errors, which are errors in the satellite's reported position, add another plus or minus 2.5 meters. Satellite clock errors add about plus or minus 2 meters. It all stacks up.
So there are all these little errors piling on top of each other.
Right. And the Wikipedia error analysis notes that when you take all of these together, civilian GPS horizontal position fixes are typically accurate to about 5 meters under a clear view of the sky. But high-end receivers using dual-frequency signals can achieve real-time positioning within a few centimeters and long-term measurements at the millimeter level, according to GPS.gov.
Millimeter level. That's insane. Who's using that kind of precision?
Surveyors, scientists, precision agriculture, construction. GPS.gov explains that survey-grade receivers use 2 GPS radio frequencies, L1 and L2, to achieve that level of accuracy. Your phone is using a much simpler setup.
Let's talk about the signals themselves for a second, because I've heard terms like L1 and L2 thrown around. What are those actually?
So, according to Wikipedia's GPS signals article, there are 4 GPS signal specifications designed for civilian use. In order of introduction, L1CA, L2C, L5, and L1C. The L1CA signal is called the legacy signal and is broadcast by all currently operational satellites. The others are modernized signals only available on newer satellites.
And the signals carry more than just a timing ping, right? There's actual data in there.
Absolutely. Wikipedia's GPS signals entry explains that the signals include ranging signals for measuring distance and navigation messages. Those navigation messages include something called ephemeris data, essentially the precise orbital information for each satellite, and the almanac, which is status information about the entire constellation.
So every signal is basically the satellite saying, here's exactly where I am, here's exactly what time it is, and here's the state of the whole network.
That's a really clean way to put it. And your receiver uses all of that to do the trilateration math. NASA describes it as the receiver determining its position by calculating how long it took for the signals to reach it, but it needs that full package of information to do it correctly.
Now, here's something I want to push back on a little. We keep saying GPS, but isn't GPS technically just the American system? There are others, right?
Yes, good catch. GPS is specifically the US system, owned by the US Space Force and operated by Mission Delta 31. But the FAA notes that there are 3 other major constellations providing similar services: GLONASS from Russia, Galileo from the European Union, and Beidou from China. Collectively, all of these are called Global Navigation Satellite Systems, or GNSS.
And all of them are free to use?
According to the FAA, all providers have offered free use of their respective systems to the international community, so your phone is potentially pulling from multiple constellations at once to get a better fix.
That actually explains why modern phones seem to lock on so fast. They're not just waiting for one system.
Exactly. And there's another piece to that, something called Assisted GPS, or AGPS. A 2026 guide on how GPS works explains that modern phones use AGPS to lock onto satellites faster by using cell towers. The cell network gives the phone a rough location and satellite data to speed up the initial fix.
So the cell towers are basically giving the GPS a head start.
Exactly. Without AGPS, your phone would have to download all the satellite data cold, which takes longer. With it, the process is much faster. But once it has the satellite lock, the positioning itself is still pure GPS, no internet required.
That's actually a misconception I had for a long time, that GPS needs data to work.
Super common misconception. The 2026 guide is explicit about this. GPS is a passive technology that works perfectly without an internet connection or cellular data. The Maps app might need data to download map tiles, but the positioning itself is completely independent.
Okay, I want to go back to something you said earlier about the ionosphere causing errors. That's the atmosphere messing with the signal?
Right. The FAA explains that the receiver must account for propagation delays, decreases in the signal's speed caused by the ionosphere and the troposphere. The signal is traveling at the speed of light in a vacuum, but when it hits the atmosphere, it slows slightly, and that tiny delay throws off the timing calculation.
And solar storms can make that worse?
GPS.gov lists major solar storms as a less common but real cause of accuracy degradation. The ionosphere is energized by solar activity, so a big solar event can significantly increase those propagation delays and throw off positioning.
So the sun can mess with your navigation. That's a fun fact to drop at a party.
It really is. And GPS.gov also notes that radio interference or jamming is another less common cause. There are actually people who deliberately jam GPS signals, which is a whole other conversation about the vulnerabilities of a system we've become completely dependent on.
That's a little unsettling. We've built so much infrastructure on top of GPS.
Aviation, shipping, financial systems, emergency services, all of it relies on GPS. The FAA has developed international standards for using these constellations in aviation specifically. The stakes of GPS going wrong are enormous.
And yet the system itself is remarkably reliable. The 2024 performance data from GPS.gov showed the constellation met almost all of its accuracy and continuity standards.
It did. The 2024 GPS SPS performance analysis, commissioned by the Space Force, concluded that all of the key accuracy assertions were met in 2024. The signal accuracy target is 7 meters at 95% globally, and the system hit that. It's an incredibly well-maintained piece of infrastructure.
Okay, I want to zoom out for a second. We've talked about the 3 segments, trilateration, atomic clocks, accuracy limits. What's the one thing you think most people fundamentally misunderstand about GPS?
Honestly, that it's magic. People treat the blue dot like it just appears, but what's actually happening is your phone is doing incredibly precise physics, measuring the travel time of radio waves moving at the speed of light, from satellites 20,000 kilometers away and solving a geometric equation to put you on a map. It's not magic, it's math and physics working perfectly together.
And the math is trilateration, knowing your distance from at least 3 known points to find your position.
Right. And GPS.gov puts it beautifully. The concepts behind GPS positioning are very simple, but the application and implementation require amazing precision. That tension between simple concept and extraordinary execution is what makes GPS so impressive.
Simple concept, extraordinary execution. I love that. So when you step back from everything we've covered today, here's what really stands out to me. GPS is this massive, expensive, government-operated infrastructure that billions of people use every single day for free, and almost nobody knows how it works.
And understanding how it works changes how you interact with it. When you know that your phone is listening to 31 satellites orbiting at 20,000 kilometers, timing radio signals to the nanosecond, and solving geometric equations to place you on a map, the blue dot stops being a given and starts being genuinely remarkable.
And it also helps you understand its limits. If you're in a canyon of skyscrapers and your GPS is off, you now know why. Multipath distortion, signal blockage, the ionosphere doing its thing.
Exactly. And if you need better accuracy, like if you're doing precision work, you now know that dual frequency receivers exist, that augmentation systems can get you to centimeter level precision, and that the basic smartphone GPS is a consumer grade version of a much more capable system.
Here's what I keep coming back to, though. This whole thing started with scientists tracking Sputnik in the 1950s. They noticed a radio signal shifting as a satellite moved overhead, and from that observation, we eventually built a system that costs $1.84 billion a year to run and is free for every person on Earth to use. That's a pretty extraordinary chain of events.
And NASA makes the point that ancient sailors would be completely flabbergasted by the speed and ease of pinpointing your location today. They spent their lives learning star charts and ocean currents. We just open an app. And somewhere above us, 31 satellites are silently doing the work, with no idea we're even here. That's the part that gets me every time. The system doesn't know you exist. It's just broadcasting constantly for anyone who wants to listen. There's something almost generous about that.
That's a great place to land. So the next time you drop a pin or ask your phone for directions, you'll know exactly what's happening. Radio waves racing down from 20,000 kilometers up, a fourth satellite quietly correcting your clock, and a geometric equation placing you on the map within about 5 meters. Not magic, just really, really good physics.
Thank you for listening to Robert Joodat Podcast. Subscribe to be notified of the upcoming episodes. Available on Spotify and all other major platforms.